Hi class! So today, here in Statics of Rigid Bodies, we are now going to discuss the method that we are going to use to analyze frames, and that is method of members. So for this lesson, student must be able to solve the internal reactions of each joint of the frame using method of member. So let's start our discussion now. Okay, so let us first discuss three-force member. So a three-force member is one subjected to three or more forces applied at different positions. It is essentially subjected to bending loads. In fact, according to the above definition, any beam is a three-force member. So basically, even a simply supported beam, okay, that's actually a three-force member. Okay, so here, um, this beam is supported by a roller at A and a hinge at B, no? So this beam carries this load P. Okay, so we know that this supports, it will provide these reactions, right? So there will be no horizontal reaction here at the hinge because there is no horizontal load, or there are no other horizontal forces involved in this system, right? So this, if we are going to count the number of forces here, there are actually three forces here. So basically, this is a three-force member. And also, if you are going to consider a beam wherein it is supported by a hinge at both ends, okay, as we can see, this is supported by a hinge here and a hinge here. So if you are going to apply a load P here, okay, so this beam, this will actually bend. Okay, so that bending action, it should be countered, okay, by the supports. Okay, so this support should provide forces that will counter the bending action of the beam. So the forces that will counter that bending will be this reaction force A, okay, theta A from the horizontal, and reaction B, and this is inclined, theta B from the horizontal. So these forces, okay, reaction A, incline, theta A. So these are unknowns, right? So this will be two unknowns. So we can actually resolve this into horizontal and vertical component, and that is AH and AV. So this is equivalent, AV and AH. This is equivalent to A and theta A. Okay, so same here with the reaction force B. We can resolve this into its equivalent horizontal and vertical component, and that will be BH and BV. So as we can see here for this beam, okay, if this load P is given, okay, there will be four unknowns here, right? So these are AH, AV, BV, and BH. But as we know, we can only generate a maximum of three equations, right, in solving for any system, right, any force system. Okay, so here, this is actually an indeterminate beam, right? We cannot solve this using statics. Okay, but as we know, members in frames, okay, they are actually three-force members. Okay, so as you can recall, frames are actually pin connected. The frames that we're going to analyze are pin connected. So meaning to say, if we construct the free body diagram of the members, okay, in a frame, okay, this will be the same free body diagram that we will see, because the members in frames are pin connected at both ends, okay, and as we know that pins are actually equivalent to hinge, right? There if it's pin connected, there will be two reaction forces as well, one horizontal and one vertical. So for this type of members, okay, we are going to solve the reaction forces using method of members. Okay, so we will now discuss method of members. Okay, if some or all members of a pin-connected structure are subjected to bending action, the structure is called a frame. So we already talked about this in the introduction, no, to analysis of structure. So for frames, it's not necessarily that all members are subjected to bending action. So for frames, it can happen that some of the members are subjected to bending, and some of the members are just subjected to actual forces. Okay, so since it is not feasible to pass a section through the members of such structure, they are analyzed by considering the separate free body diagram of each three-force member. The procedure is called the method of members. So for frames, we cannot apply method of joints and method of section. Okay, so apply method of joint because for method of joints, we know that for trusses, the forces are just, or the members are just subjected to axial forces, and that axial force, we just transmit that to the joint. But here in frames, the members are not just subjected to axial forces, so we cannot do that. We cannot apply method of joint. Okay, and also for method of section, in trusses, using method of section, we cut the truss into sections, right? And we know that the cut members in that truss, okay, in that section, it will just give us an actual force, a single force, okay, for each member. Okay, but here in frames, if we are going to cut the section, okay, of a frame, or if we cut a frame into sections, okay, we will see that the cut members, okay, it will not just give us an actual force, a single force. Okay, in fact, if we cut the member, okay, of a frame, there will be three forces that we can see: one horizontal reaction, uh, vertical force, horizontal force, vertical force, and a moment. Okay, so if you are going to cut, let's say, three members, okay, there will be 9 unknowns, because for each member, it will give you a horizontal force, a vertical force, and a moment. Okay, so it will not be feasible, okay, if we use method of section in analysis of frames. Okay, so what we are going to use, or the method that we are going to use, okay, to analyze frames is called method of members. So in method of members, basically what we are doing here is we are separating the free body diagram of each member. And we know that for frames, uh, the members here are 3/4 member, right? So we will disassemble, okay, the members in a frame, and we will analyze the free body diagram of each member, okay, and from that we will solve that, no? So this method, we oftenly call this as backlash method, okay, because binabaklas natin, or we are disassembling the the members here, okay, and analyze the free body diagram of each member. Okay, and from that we start solving, no, sa the forces involved in each free body diagram. Okay, so the essential principle involved in drawing the free body diagrams of the several members of a frame is that of action and reaction. When separating the members for analysis, the force exerted by the pins must be consistently represented as acting in opposite directions on the separated members. Okay, so it will be important here, okay, that we are consistent, okay, with the directions of the reaction forces involved in the free body diagram of each member. Okay, so let's say we have a free body diagram of a member, okay, and there will be reaction forces that will act on that member, okay, which will be that reaction force that can be common to another free body diagram, meaning to say it can also act to another free body diagram. Okay, so if we are going to transfer that reaction force, okay, to another free body diagram, that reaction force should be directed oppositely. Okay, so we have to be consistent with that. Okay, so that if we transfer a reaction force from one free body diagram to another free body diagram, it should be directed oppositely. So we will use that concept here for method of members. We actually use that in method of joint, right? That if we transfer, let's say, the actual force acting on a member, if we transfer that to the free body diagram of the joint, it is actually directed oppositely, right? So same with this, no? So we will apply that concept. Okay, and also, as a general rule for method of members, it is best to solve first for the unknown quantities common to both free body diagrams. So this is what we are going to do here. Okay, we are going to solve first for the unknown forces, okay, that are common, okay, to one free body diagram and another free body diagram. Okay. Okay, so here are the steps that we are going to use for method of members. So the first one, if applicable, solve first the reactions of the supports from the free body diagram of the entire structure. Okay, so the second step, start with the member that carries a load. Draw its free body diagram and solve for the unknown forces. So we are going to start with the member that carries a load because if we are going to draw the free body diagram of a member, okay, we are going to assume the direction of the reaction forces. Okay, so if you're going to assume the reaction forces, we should base our assumption to the load applied to that member. Okay, so we are going to solve for the unknown reaction forces for that member using either the principle for equilibrium of parallel force system or equilibrium of non-concurrent force system. So we are going to apply those principles. Okay, so for number 3, after determining the forces on the member from step 2, proceed to the next member where the solved reaction forces from step 2 also act. Draw its free body diagram and solve the unknown. So the reaction forces that we solve from step 2, okay, from that member, okay, we are going to use that, okay, in solving for the free body diagram for the unknown forces in the free body diagram of another member. Okay, so again, we are going to use that principle that if we transfer a force or a reaction force from one free body diagram to another free body diagram, it should be directed oppositely. Okay, so we have to be consistent with that. So for our fourth step, we just repeat step 3 until you solve all the needed reaction forces. Okay. Okay, so let's proceed now to sample problem number 1. The A-frame shown supports a 600-pound load and has the given dimensions. Neglecting the weight of the members, compute the values of the forces acting on the pins B, C, and D. So we have here an A-frame. Okay, so this A-frame is supported by a roller here at A and a hinge here at E. Okay, so for member BD, okay, this carries a 600-pound load. And this member BD, this is actually supported by member AC and member CE. Okay, so what we're going to do here is solve for the forces acting on the pins B, C, and D. Okay, so take note here that we are going to to neglect the weight of the members. Okay, but there will be problems here, okay, in method of members for analysis of frames that the weight are considered. Okay, so you have to be careful with that, to include that in our solution. Okay, so let's start solving this. Okay, so again, we are asked here to solve for the forces acting on the pins B, C, and D. So here are the pin uh, B, C, and D. So to solve this, okay, we are going to follow our procedure here. Okay, so the first thing that we have to do is construct the free body diagram of the entire structure. So we have to analyze if we can solve, okay, for the reactions at A and reactions at E. Okay, so constructing the free body diagram of the entire structure. So this will be the free body diagram. We know that we will have a reaction here at A. Okay, so this is just a roller, so there will be a single reaction here. And then we have here two reaction forces here at E, EV and EH. Okay, but here, to solve for the reactions, okay, let's say for reaction A, we can solve this by taking up moment here at E. Okay, so taking up moment here at E, that will just be RA times its moment arm, which is 20, minus 600, which is the load here. Okay, 600 and its moment arm will be 8. So that will be equal to 0. So solving for RA, it will just be 240 pounds. So if we input that in our calculator, again, 600 times 8 divided by 20. So that is 240 pounds. Okay, so that will be the reaction at A. Also, for reaction at E, okay, we can just sum up forces vertical here. Okay, so summing up forces vertical, that will just be RA minus 600 plus EV, and that will be equal to 0. So we already have RA, which is 240. So we can solve for EV here. That will just be 600 minus 240, right? So that will just be 360 pound. Also for some EH, no, as we can see here, there are no other horizontal forces here. Okay, so we know already that EH is just equal to 0. Okay, so from here, no, since we already solved for these reactions, we can now start solving this frame. Okay, we can now start with the member that has that is carrying a load, and that is member BD. Okay, so drawing the free body diagram of member BD. Okay, so this will be the free body diagram. So BD, okay, it carries this 600-pound load. So this member, it will be subjected to bending. Okay, so it is mentioned in the problem, okay, that the weights of the member will be neglected, okay, but there will be cases, okay, that we will consider the weight, okay, if it's mentioned in the problem. So don't forget to include that, okay, if it's given. Okay, so here, since the member will be subjected to bending, of course, it should be countered by the support, which is pin, no? So these two pins, okay, they will provide two reaction forces each. Okay, so for pin here at B, it will provide a horizontal reaction and a vertical reaction. Same here with pin at D. Okay, so from here, we can actually solve, okay, for some unknown reaction forces here. So we will start solving for BV and DV. Okay, so to solve for BV and DV, we can actually take a moment. Okay, let's say we take moment here at D, we can solve for BV. Okay, and if we already solve for BV, we can solve for DV by summing up forces vertical. So let's start our solution here. Okay, so for BV, to solve for BV, we can take moment here at D. Okay, and DH will just be cancelled, and DV, of course, and BH, it will also pass through point D, so it will also be cancelled. So taking up moment at B, that will just be BV times 12. That will be the moment arm, 8 plus 4, minus 600 times 4. Okay, and that will be equal to 0. So we can directly solve here for BV. Okay, so we cannot box this already, because the items that we are asked here are forces, so it should be reaction forces. So this is just a component, so we have to solve first for BH. Okay, to solve for the resultant of reaction at B, no, reaction force at pin B. Okay, so after we solve for BV, we can solve for DV by summing up forces vertical or summing up moment here at B. So it's your choice. It depends on you. So we just sum up forces vertical here. So summing up forces vertical, that will just be BV minus 600 plus DV is equal to 0. We already solved for BV, and that is 200. So solving for DV, it will just be 400 pound. Okay. So also, if we sum up forces horizontal here, it will just be DH minus BH, and that will be equal to 0. But we don't know yet, okay, the value of DH and BH. We just know that DH is just equal to BH. Okay. Okay, so we already solved for some of the forces in member BD, right? So we already solved for BV and DV. So we can now proceed to another member. So we can either proceed here at member AC or member CE. So here, we're going to proceed here at member AC. So constructing the free body diagram of member AC. So this will be the free body diagram. So we know already, and we solve already for the reaction here at A, and that is 240 pound. Okay, so here at pin B, no, we know that from member BD, okay, the reaction force here at B is the BH is directed to the left and BV is directed upward, right? So that direction, if we transfer that here, here at member AC, it should be directed oppositely. So BH should be directed to the right and BV should be directed downward. Okay, so we already solved for for BV, so we will use that here. And also for pin at C, okay, so the reaction forces here will be CH and CV, and we will just assume their direction. So CH, we will assume it as directed to the left, And CV, we will assume it as ano, downward, no? So from here, we can see that there will be three unknowns, CV, CH, and BH. Okay, again, we already solved for BV, so we are going to use that here. Okay, so since there will be three unknowns, we have to generate three equations here to solve these unknowns. Okay, so to solve for, let's say for BH, no? So to solve for BH, we can take moment here at C. So if we take here, take moment here at C, CV and CH will just be cancelled and the only unknown will be BH. Okay, so taking up moment here at C, so that will just be 240 times its moment arm. So its moment arm, we solve this no, from the given structure, okay, from the dimensions here. So we know that this is 45 degrees here, so this will also be 45 degrees here. And also, if this is 45 degrees here, this will also be 45 degrees here, right? So, this total distance, this is actually 4 plus 8 plus 4 plus 4, so that will be 20. Okay, so, its midspan, this will be its midspan, right? So, its midspan, that will just be 20 divided by 2. Okay, and this distance is actually this distance. Okay, so that will be 10. So that will be the moment arm of 240. So that will be positive since it will be clockwise from point C, no? Its rotation about point C. Okay, and also for BH, its moment arm will be this distance. So from the figure, again, so if this is this ano no, this side, this is actually 8 plus 4, so this is 12. So its midspan. Okay, this is actually just the, 12 divided by 2, so that will be 6. So this side, okay, so this side will be 6. So if this side is 6, okay, since this is 45 degrees, if we put a line here, no, so that will be the opposite side of this triangle. Right? So this will be the adjacent and this will be the opposite side. So we can use tangent here, tangent of 45 degrees. That will be opposite over adjacent. So the adjacent is 6. So if we solve that, the opposite side will just be 6. Okay, so this side will be 6. So that will be the moment arm of BH. So that will be BH times 6. And it is negative since it is counterclockwise. Okay. Okay, so for BV, okay, its moment arm, this is 6, no? So I already mentioned that here, no? So this side is 6. Oh, so that will be 6. Okay, and that will be negative also because it is counterclockwise, and this will be equal to 0. So we already solved for BV, so we can directly solve here for BH. So BH will just be 240 times 10. We try to input that in our calculator. 240 times 10 minus 200 times 6. So we transpose BH and BH times 6 now, so that will be positive. Okay, so again, 240 times 10 minus 200 times 6 divided by 6. So that will be 200. Okay, so BH will be 200 pound. Okay, so no need to ano ha to include here if the force is directed to the right or to the left. So no need to write that. So BH is 200 pound. Okay, so also to solve for CH. Okay, since we already solved for BH here, so we can directly solve for CH. So that will just be BH minus CH is equal to 0. We already solved for BH. So basically, CH will just be equal to 200 pound. Okay, so okay, so let's proceed now. Summation of forces vertical. So summing of forces vertical, we already have BV. Okay, and the only unknown will be CV. So we can solve for CV directly here. So that will just be 240 minus BV minus CV. So substituting the value of BV, which is 200. So solving for CV, that will just be 40 pound. Okay, so we already solved for CH and CV. We can actually solve for its ano, reaction force. Okay, so for its resultant ano, no, reaction force, that will just be square root of CH squared plus CV squared. So that will be the answer for reaction at C. Also for BH, we already solved for BH and BV. So we can solve for the resultant of its reaction force, no, at B. Okay, so let's proceed now to the free body diagram of member CE. So this will be the member CE. So the reaction force here at point D, no, we will just transfer the reaction force from the free body diagram of member BD. Okay, so this will be directed oppositely here. So DV will be directed downward and DH will be directed to the left. Okay, so also for CH and CV here, we will just transfer CH and CV from the free body diagram of member AC. So it will be directed oppositely. CH will be directed to the right and CV will be directed upward. Okay, so from here, we already know the reaction here at E, and we know that the horizontal reaction is 0. So this will just be 360 pound upward here. Okay, so from here, we already solved for CV, right? We already know the value of CV. Okay, so we can solve for DV by summing of forces vertical, right? And we already solved for CH, so we can directly solve for DH, right? We already know CH, so we can directly solve for DH. And sige, let's do this. So there will be two unknowns here, right? Uh, one unknown rather. DV na lang pala, at saka DH. Dalawa pala. Two unknowns. Okay. DV, we already solved for DV, actually. Right? So, sige, let's do this. So, summing of forces vertical, this will just be 40 minus DV plus EV is equal to 0. So, we already solved for DV actually from the free body diagram of member BD. So, this will just be for checking. No? So, EV, this is the reaction, this reaction. So, this will just be for checking. Okay, so 40 minus dV plus 360 solving for dV, this is just 400 pound. Okay, so we already solved for dV and this is actually the same answer. So we can say that our answer for dV is correct since it is consistent here. Okay, so also some from the free body diagram of BD, no? So we already know that BH is equal to DH is equal to BH. So DH will just be 200 pound. Also here, actually, if we sum of forces horizontal from this free body diagram of member CE, that will just be DH is equal to CH. Okay, and we know that CH is 200 pounds. So basically, DH is really 200 pounds. So we can use that for checking also. Okay, so from here, we already solved for all the component forces of the reactions at B rather, B, C, and D. So we will just solve for the resultant forces since we are asking for the forces, not the components of the forces. So solving for the reaction at B, okay, that will just be square root of BH squared plus BV squared. So that will be 282.84 pound. So that will be the answer. So you can box that already. Now for the reaction force at C, again, that will just be square root of CH squared plus CV squared. So that will just be 203.96 pounds. So you can box that. And for reaction at D, reaction force at D, that will just be square root of DH squared plus DV squared. So solving for that, that will just be 447.21 pounds. So this will now be the answers for this problem. Okay, so we will proceed now to sample problem number 2. The structure shown is hinged at A and C. Find the horizontal and vertical components of the hinge force at B, C, and A. Okay, so here, we have here a frame. No, so we know that this is a frame because there is a 200-pound load here, no, applied within the span of this member. So this will be subjected to bending. So this is a frame. Okay, so this frame is supported by hinge at C and a hinge at A. Okay, so there's also a 100-pound load here. So we are going to solve for the reaction force or force here at B, join C, B, join C, and join A. Okay, so here, no, in this problem, okay, there's no given weight for the member. So we will not include the weight of the members here, no. So let's start our solution for this. So again, this is our given truss, okay, and we are going to solve for the horizontal and vertical components of the hinge force at B, C, and A. Okay, so for our first step, we will try to solve for the reaction force, okay, using the free body diagram of the entire structure. But here, the free body diagram of the entire structure here, C is hinged and A is also hinged. So this will be the reaction forces here. Okay, as we can see here, if we take, let's say if we take moment at C, okay, there will be two unknowns, AH and AV, right? So there will be no we cannot solve the reactions from the free body diagram of the entire structure. So we can now proceed to solving the free body diagram of the member. So we will start with the member that carries a load. So we can actually start either member AB or member BC, no? So here, let's start with member BC. So constructing the free body diagram of member BC. Okay, so this carries a 200-pound load. So this will be the reaction at C, CV, and CH. And for B, this will be the reactions here. Okay, so here, if we take moment, let's say here at C, we can solve for BV. And if we solve for BV already, we can solve for CV, no? So that's what we are going to do here to solve that. So we will take moment at B, okay, to solve for CV. So taking up moment at B, that will just be CV times 10 minus 200 times 5, so that will be equal to 0. So CH and BH, they will just be cancelled because they will pass through point B. Okay, so we can solve directly for CV here. So solving for CV, that will just be 100 pound. Okay, so we can already box this already since this is already a vertical component, no, of force here at C. So we can already box that. Okay, so summing of forces vertical, we can solve for BV. So that will just be CV minus 200 plus BV is equal to 0. So solving for BV, since we already have CV, that will be 100. So solving for VV, that will also just be 100 pound. Okay, so we can already box that. Okay, so CH and BH, if we sum of forces horizontal, we will just know that they will just be equal. But we don't know yet their value. Okay, so we will just leave it here that BH is equal to CH. So we can now proceed to another free body diagram. Okay, so constructing now the free body diagram, okay, of member AB. Okay, so this is member AB. So we will just transfer BH and BV from the free body diagram of member BC. So this will be directed oppositely. Okay, so we already solved for BV. So the only unknown here is BH and this reaction forces AV, AH and AV. Okay, so there will be three unknowns here. BH, AH, and AV. So we can solve this by generating three equations. Okay, so we will take moment here at A. So if we take moment here at A, AH and AV will be cancelled. And the only unknown here will be AH since we already solved for BV. Okay, so BV, its moment arm will be 6. Okay, so this is given from the figure. So BV times 6 minus BH, its moment arm will be 8. Okay, plus 100. Okay, and its moment arm will also be 6 plus 2, so that will be 8. So that will be equal to 0. So we already have BV, that is 100. So we just substitute that. And solving for BH, that will just be 100 times 8 plus 100 times 6 divided by 8. So that will be 175 pounds. So we can already box this. Okay, so we can also solve for AH, no, by summing of AH rather, no, by summing of forces horizontal here, no. So we already solved for BH, so we can solve for AH. So solving for AH minus BH is equal to 0. So AH will just be 170 pound as well. Okay, so we already solved for for this. So we can already box this AH. Okay. So also for summation of forces vertical, that will just be AV minus BV minus 100, and that will be equal to 0. And we already solved for BV, that is 100. So we can directly solve for AV. AV is equal to 200 pounds. So we can already box that. Okay, now let's proceed to FBD of member, no, from the FBD of member BC, okay, we know that BH is equal to CH. Okay, so since we know that BH is 175 pounds, so therefore CH will just be also 175 pounds. So this will now be the answer. Okay, so let's proceed to sample problem number 3. A 3-hinge arc is composed of two trusses hinged together at B. compute the components of the reaction at A, and then find the forces acting in bars AB and AC. So hint, first isolate each truss as free body. Okay, so we are going to apply method of members here in such a way that we are going to disassemble. Okay, we are going to separate the free body diagram of the truss here at the left and the truss here at the right. So since they are connected here at D, no, and this support at D, this is a hinge, no. So this is a three hinge arc. This is hinged here, and also hinged here. Okay, so we can separate the free body diagram of these two trusses here. Okay, the truss here at the left and the truss here at the right. So we are going to compute the components of the reactions at A. Okay, so we are going to solve for the reaction of this support, no? And we are going to find the forces acting in bars AB. So bar AB, so this is bar AB, and bar AC. So this is bar AC. Okay, so let's start solving this. Okay, so again, these are the forces that we are going to solve here, the components of the reaction at A, okay, and the forces acting in bars AB and AC. So here, we are going to solve first for the reaction forces, no, from the free body diagram of the entire structure. Okay, so this will be the free body diagram of the entire structure. So we have here AH, AV, and then GV and GH. Okay, so we can solve for AV by taking up moment here at G. So since what we need here is just components of reaction at A. Okay, so we can just solve for AV, no, by taking up moment here at G. Okay, so that will just be AV times its moment arm, which is 20 plus 20 plus 20 plus 20, so that will be 80. Minus 360, its moment arm will be 60, that is 20 plus 20 plus 20. And then minus 600, its moment arm will be 20, and that will be equal to 0. So solving for AV, okay, we can directly solve that. So AV will be 420 pounds. So we can already box this since we are solving for this, no, components of the reaction at A. And then we are now going to construct the free body diagram of the left part of the truss. Okay, since we have to solve for AH, no? So we cannot solve AH by from the free body diagram of the entire structure. So we will just know that AH is equal to GH, but we don't know the value. So we will now proceed here, no, at the free body diagram of the left part of the truss. And also, we are also solving for bars AB and AC. So what we just need here is the free body diagram here, no, at the left nga. Okay, so this will be the free body diagram. So we separate this, no, so we can do that, no, since it is hinge connected here at D. So this will be the free body diagram, no. So here at point D, so there will be two reactions here, DV and DH. Okay, and then we have here AH and AV. So we already solved for AV. So if we take moment here at D, we can directly solve for AH. Okay, so taking up moment at D, so that will just be AV times its moment arm, which is 20 plus 20, minus AH times its moment arm, which is 30, minus 360 times 20, and that will be equal to 0. So we already have the value of AV, which is 420. So we can directly solve for AH, and AH will just be 320 pounds. So we can box that already. Okay, so also we have to solve for the bars, for the forces acting at bars A, B, and AC. So we will apply method of joint here. Okay, so applying method of joint. Okay, so this will be the free body diagram of joint A. So we have here AH and AV. And then our for AB here, so its slope, no, it's not given, but we can get that from the figure, no. So our slope here, so this is 30, no, the height is 30, and this side is actually 40, no. So reducing that, so that will be 3 rise and 4 run, and then the hypotenuse therefore of that slope triangle will just be 5. So we will assume the direction or
the actual force AB or AC, whether in compression or tension. For AB, we will assume it as ano no, as compression. So this should be directed downward since the vertical force here is upward, no. So it should counter that. And for AC, we will just assume it as ano, as compression, tension rather. Okay, so there will be two unknowns here, AB and AC. We already solved for AH and AV, right? So from here, summing of forces vertical, we can directly solve for AB. So that will just be AB minus AB 3 times 5. So that will be the vertical component of AB. So that will be equal to 0. So substituting AV, which is 420, so we can directly solve for AB here. So AB will just be 420 divided by 3 over 5, right? So that will just be 700 pounds. So this is positive, no? The answer is positive. So our assumption for AB is correct. So that is in compression. Okay, so we can now box that. Okay, now for member AC, we can just sum up forces horizontal here. So this will just be AH plus AC minus AB 4 times 5, which is the horizontal component of AB. Okay, and that will be equal to 0. So we already have the value of AH and AB. Okay, we can directly solve for AC. So solving for AC, that will just be 240 pounds. And that is in tension since the answer is positive. So our assumption is correct, which is in tension. Okay, so we can already box that. So these are already the answers for this problem. Okay, so let's proceed now to sample problem number 4. A beam carrying the loads shown is composed of 3 segments. It is supported by 4 vertical reactions and joined by 2 frictionless hinges. Determine the value of the reaction. So we have here a beam, and this beam is composed of 3 segments. So this is the first segment, this is the second segment, and then this is the third segment. So this beam, no, these segments, okay, are joined by 2 frictionless hinges. So these are the frictionless hinges. So these are internal hinge. Okay, so for internal hinge, okay, so this will be the same with the normal hinge. Okay, so if we separate the free body diagram of these segments, okay, we will see that here at this internal hinge, there will be 2 reaction forces, one horizontal and one vertical reaction. Okay, so that's how we will do that, no, for internal hinge. Okay, so let's start solving this. Okay, so for this problem, we are going to solve for the reactions R1, R2, R3, and R4. So obviously, if we consider the free body diagram of the entire structure, okay, there will be 4 unknowns. So we cannot solve this, okay, by using the free body diagram of the entire structure. So we have to use method of members here, no? So we can separate the free body diagrams of each segment. Okay, so we will start with the segment 1. Okay, so for the free body diagram of the first segment, so this is the first segment. Okay, so for this first segment, so this is connected here by a hinge, no, by an internal hinge. So for an internal hinge, okay, so there will be 2 reactions here, one horizontal and one vertical. So there will be AV and AH here. But since we know that there's no other horizontal forces here involved in this system, so AH will obviously be just equal to ano, to 0. Okay, so there will be 2 unknowns here, so we can apply equilibrium of parallel force system here, right? So we can take moment here at A. So this is point A, no? Let's say this is point A. Okay, so we take moment here at A, so we can solve for R1. So solving for moment at A, so that will just be R1 times 6 minus 400 times 3, and that will be equal to 0. So AV will just be cancelled since we take moment here at A. Okay, so we can directly solve for R1. So R1 will just be equal to 200 pound. Okay, so we can already box that. Okay, and also summing of forces vertical, we will solve for AV, no? So that will just be R1 plus AV minus 400. So R1 is 200, so we can solve for AV, and that will just be 200 pounds. So no need to box that because we are not solving for that. We are just solving for R1, R2, R3, and R4. So this AV, we will use this, no, to the free body diagram of the second segment. Okay, so for the second segment, if we cut this, no, if we draw its free body diagram, so we will have AV here, but we will also need the reaction here, no? So let's say this is point B. So let's say this is point B. So there will be BV rather, BV and BH. We know that BH will just be 0, but we don't know yet the value of uh, BV, right? So there will be four unknowns, BV, R2 and R3. Three pala. There will be three unknowns, R2, R3 and BV. But this is parallel force system actually. So we can only generate two equations here. Summation of forces vertical and one moment equation. So there are three unknowns. So for that, now we will proceed first to the free body diagram of the third segment. So we will solve first for BV, okay, before proceeding to the free body diagram of the second segment. So here for the free body diagram of the third segment, we have here 100 pound per feet uniform load, and then we have here R4, and BH will just be equal to 0 since there's no other horizontal forces here. So we can solve for R4 by taking moment here at B. So taking moment here at B, that will just be, okay, so for this 100 pound per feet uniform load, okay, so we will resolve this into its equivalent point load. So that will be 100 times 6. No, so its point load is located at the midspan since this is just a uniform load. So the moment arm here will just be 3. Okay, so minus R4 and its moment arm is 6, and that will be equal to 0. So solving for R4 here, so that will just be 300 pound. Okay, so we can already box that. So we are solving for R4 here. Okay, so also we can solve for BV by summing up forces vertical. So that will just be BV minus 100 times 6 plus R4 is equal to 0. So we already have R4, so solving for BV, that will just be 300 pound. Okay, so no need to box that. We are not solving for BV. Okay, so we will just use BV for the free body diagram of the second segment. So we will just transfer BV and AV to the second to the free body diagram of the second segment. So if AV is directed upward here, it should be directed downward here. Also for BV, if it's directed upward here, if we transfer that to the free body diagram of the second segment, it is directed downward here. Okay, so AH and BH will just be 0. So there will be two unknowns here, R2 and R3. Okay, so we can use equilibrium of parallel force system here. No, so we can take moment here at R3, no, to cancel R3. So we can solve for R2. So taking up moment at R3, so that will just be negative AV times 14. The moment arm of AV is 14 plus R2, its moment arm is 10 minus 200 times 40. So we will resolve this uniform load into its equivalent point load. So its equivalent point load will be 200 times 14. Okay, and its moment arm, so since this is 14, no, so it will be applied, the point load will be applied 7 feet, no, from here. So that will be 7 feet, the moment arm, plus BV. So BV, its moment arm is 4. So this will be equal to 0. So we already solved for AV and BV. So we will just substitute that here. So we can solve for R2 here. So solving directly for R2, okay, that will just be 2,120 pounds. So we can already box that. Okay, now for the remaining unknown reaction, that is R3. So we can just sum up forces vertical here. So summing up forces vertical, that will just be negative AV plus R2 minus 200 times 14 plus R3 minus BV is equal to 0. So we already have AV, R2, and BV. So we can directly solve here for R3. So solving for R3, that will just be 1,180 pounds. Okay, so here we already solved for R1, R2, R3, and R4. So the way for us to check if these answers are right, so we can sum up all these reaction forces. Okay, so we can sum them up. So that will just be R1 plus R2 plus R3 plus R4. So that should be equal to the resultant of the applied loads. Okay, so the applied loads will be 400 pound plus, we resolve this into point load, so that will be 200 times 14, and then plus we also resolve this to point load, that will be 100 times 6. So the resultant of that applied load, of those applied load, should be equal to the to the reaction, to the resultant of the reaction forces. So you can check that. So let's proceed now to sample problem number 5. The frame shown in the figure is hinged to rigid supports at A and E. Find the components of the hinge forces at A and E and the forces in member BC and BD. Okay, so for this given frame, okay, so this is supported by a hinge here at A and also a hinge here at E. Okay, so if you're going to analyze the members of this frame, so as we know, member AB, okay, so since there is an applied load here, okay, within its span, so member AB will be subjected to bending. Okay, so also for member CE, so this is member CE. Okay, so there is a member attached within the span of member CE. So member CE will also be subjected to bending, right? So it will be subjected to bending. Now, for member BD, so this is member BD. So here, it's not mentioned in the problem that we will include or consider the weight, okay, in the in the members, right? So we will neglect the weights here. Okay, so here at member BD, so this member BD, there's no actually applied load here. Okay, there's no applied load within the span of member BD, right? So weight will also be neglected. So meaning to say, this member BD will not be subjected to bending, right? This will not be subjected to bending, so this will just be subjected to axial force, either compression or tension, right? That's why we will just compute for the axial force for member BC here, no, in this question. Okay, in this problem. Also for member BD, so for member BD also there's no load applied within the span of this of this member. So this will not be subjected to bending. So this will just be subjected to axial force, either compression or tension. Okay? So this will be the forces that we are going to solve. So the hinge forces at A. So here at point A and E. And we are going to solve for the reaction force or the forces here in member B, C, and B, D. So we will start our analysis here. Okay, so for this sample problem, so again, we are going to solve for the components of the hinge forces at A and E and the forces in members BC and BD. So we already know that member BC and BD, the forces that will act, okay, in these members will just be axial forces. It will just be either compression or tension. Okay, so we will start solving this um, by solving the forces that we can solve from the free body diagram of the entire structure. So this is the free body diagram of the entire structure. So for hinge at E, so we know that there will be two reaction forces here, EH and EV. And also for A, so this is hinge, so there will also be two reaction forces here, one horizontal and one vertical. So since we assume EH as directed to the right, so of course, the only horizontal force that will counter that will be AH. So AH should be directed to the left. So okay, here we can solve for for what for some forces here. So if we take moment at E, we can actually solve for AH. So if we take moment here at E, of course EH and EV will be cancelled. AV will also be cancelled. So the only unknown will be AH. So we can directly solve for AH. So that will just be negative AH times its moment arm. So its moment arm will just be 4. And then plus 120. So the moment arm of 120 to point E will just be 4 also. So here AH will just be equal to 120 pounds. So the answer here is positive. So meaning to say our assumption for AH is correct. Okay, it is directed to the left. Okay, so we can actually box this already since we are solving for this force from the problem components of hinge force at A. Okay, so we can also solve for EH by summing of forces horizontal. So that will just be EH minus AH is equal to 0. So EH will just be 120 pounds. So we can already box that. Okay, so now we can now proceed to the free body diagram of, let's say we just we just show muna, we just show the FBD of BD and BC. So we know that the forces that will act on member BC and BD, they will just be actual forces. So for the free body diagram of member BD, so this will be the free body diagram. So we assumed it as as member BD will be subjected to compression. So compression is the assumption here. For FBD of BC, okay, so for member BC, we assume also that it will be subjected to compression, no? So axial forces, this will just be subjected to an axial force, no? Okay, so let's proceed. Okay, so we will now proceed to the free body diagram of member AB. Okay, so this will be the free body diagram of member AB. Okay, so we know that here at A, the reaction forces are AH and AV. Okay, so we have here 120-pound load, and here at at point B, so BD will just provide an axial force, no? So this will be the force. So we assume BD as compression, okay, and BC we assume also as compression. So this will be the reaction forces for BD and BC. Okay, so we already solved for AH, right? So we already solved for AH. So if we sum forces horizontal here, we can directly solve for BD, right? So we will start our solution by summing up forces horizontal. So that will just be negative AH plus BD. So the slope of this this member BD, no, that will just be 4 for rise and then 3 for run. So 4 and 3, and the slope triangle will just be 5. Okay, so solving for BD, since we already have AH, so BD will just be 200 pounds. So our assumption for BD is compression, no? So since the answer is positive, meaning to say our assumption is correct, so BD is really in compression. So BD is 200-pound compression. So we can box that already. Okay, so since we already solved for BD, no? So actually we can solve for AB, no, by taking up moment here at B. So if we take moment here at B, BD and BC will just be cancelled, so we can directly solve for AV, right? So taking up moment at B, so that will just be AV times 8 minus 120 times 4, and that will be equal to 0. So solving for AV, that will be 60 rather. That will be 60 pound. Okay, so we can already box that, no? So we are solving for that. Okay, so now since we already have AV, we already solved for BD also. So the only unknown here will be BC. So if we sum up forces vertical, we can directly solve for BC. So that will just be AV minus 120 plus BD times 4 over 5. So that's the vertical component of BD plus BC is equal to 0. So substituting the value of AV and BD, we can directly solve for BC. So solving for BC, that will just be negative 100 pounds. So our answer here is negative. So meaning to say our assumption for BC is wrong. Okay, so BC is not subjected to compression. So BC, okay, is actually in tension. No, so BC is 100-pound tension. Okay, so we can box that already. And if we redraw the free body diagram of member BC, so this is actually subjected to tension. So it will be the directed this way, no, force BC. Okay, so also, if we redraw also the free body diagram of member AB, so BC, okay, it should be acting away from the joint, no? So this, since it is in tension, so this should be redrawn this way. Okay, so from here, we actually solve for, the only force that we need to solve is actually EV, right? Ito na lang, member force EV, no? We already solved for AH. So from the free body diagram of the entire structure, we already solved for AV, right? So we already solved for AV, that is 60 pounds. So if we sum up forces vertical from the free body diagram of the entire structure, okay, that will just be AV plus EV minus 120, and that will be equal to 0. So we already have AV, no, and that is 60. So solving for EV, that will just also be 60 pounds. So this will now be the answers. Okay, so that concludes our discussion for this topic. I hope that you learn. Okay, and there will be assessment tasks for this topic. So see to it that you answered that and you will submit that on our next meeting. Okay, so see you again, class. God bless you and keep safe. Bye-bye.